at the program.
Okay, good. So first, exam 3 is on Monday. And the topics, there's not going to be any rotating coordinate systems on it. So just linkages. Okay, up through linkages. Any questions about the test? Yes? No? Yes, almost? Oh. Yeah, up through linkages. And remember that old stuff can be on it too. Okay, so I had a couple of homework questions. So let's start with number 3. Oh, and about the test. So if you have any questions, linkages are going back a week or 2 or whatever, but if any questions come up as you're getting ready before Friday, feel free to ask questions on Friday related to the exam. Also on Friday, somebody from Twin Cities Engineering is going to come talk to the class for a little bit. So get a little information about Twin Cities Engineering. Who knows about Twin Cities Engineering? Anyone? Luna, you know, right? Okay, I knew it. Yeah, Twin Cities Engineering is cool, so that'll be interesting. Okay, so number 3. So this thing, the disk is rotating about the y-axis with an angular velocity of 0.1 t, which means that that speed is getting faster as time goes by, that angular speed. Okay, and this arm, if you think of this angle as theta, is oscillating. Okay, between, this is in radians, so it's oscillating between 57 and negative 57 degrees as time goes by. Okay, so it's like this thing's spinning around, the disk is spinning around, speeding up, and the tail is wagging up and down. Okay, and we want to calculate the acceleration, use the coordinate, calculate the acceleration of the end of the arm at the instant t equals 5 seconds. Okay, the end of the arm, so we're looking for this point P. The coordinate system you're going to use is shown there. We know we're going to use a rotating coordinate system, so acceleration of P is equal to the acceleration of P that's observed in the coordinate system plus omega dot cross P plus 2 times omega cross the velocity of P that's observed in the coordinate system plus omega cross quantity omega cross P. And let's start figuring this stuff out. We're only trying to calculate this at a single instant. Like you could imagine an expression, coming up with an expression for this as a function of time. We probably could do that. Nothing occurs to me as something preventing us from doing that because we have this stuff as functions of time. Maybe let's try that and see what happens. Maybe we'll run into something that gets crazy or something, but I'm not seeing what would do that. Okay, so our coordinate system is fixed to the disk. So the angular velocity of the coordinate system is 0.1 t 0. And omega dot, that means, is 0.10. The position the length of that arm is 0.3. The radius of the disk is 0.5. So if you want to get to that point P, that position vector is going to be 0.5 in the x direction plus 0.3 times cosine of theta sine theta 0. And we can express that as, so add these things up. You got, bless you, 0.5 plus 0.3 cosine of, now I'm replacing that theta with what it is, sine of t. And then 0.3 sine of sine t. That is the position according to that coordinate system. That means that the observed, so essentially what I've done is change this. So if we did it instant by instant, we'd kind of want to think of it this way. Since I'm setting it up to do it in terms of functions of time, we have functions of time, I'm going to think of it this way instead. And this is the time derivatives of the position. Okay. Well, now calculating those components double dot and those components dot is easy because we just have a function of time. So components dot is, let's see. So we have 0.3 times the cosine of time times the negative sine of sine t. And then for the y component, we have 0.3 times the cosine of time times the cosine of the quantity sine t. Okay, Nobody noticed any dumb mistakes on that derivative or anything, did you? You follow where I'm going with all this? And now the double dots. So that is negative point, no, cosine. So now this is, the derivative of cosine is negative sine. So we got 0.3 sine of t times sine of sine t minus 0.3 cosine of t squared times cosine, what happened? That did not help my train of thought. 0.3 times sine of t times sine of sine t. And then we have minus 0.3 cosine of t squared times cosine of sine t. Does that seem right? And then for the second one, we have 0.3, negative 0.3 sine t times cosine of sine t. And then minus cosine squared of t times cosine, times, so that's the minus cosine squared of t times sine of sine t. That one got a little messy. But that seems right, doesn't it?
Is it minus or plus side?
On the second term? This time, we're not taking the derivative of cosine t. We're taking the derivative of cosine of sine of t. So we get the negative from the cosine, but we don't get another negative from the sine, so I think that's right.
Should we have a factor of 0.3?
Yes. That's implied. Well, now this would get, I guess this looks a little messy, but this one you only add, so maybe that's not so bad. So the acceleration of p is equal to this thing, I'll call that, I'm going to call that capital A of t. Plus 0.10 crossed with the position vector. .5 plus 0.3 cosine of sine t, and then 0.3 sine of sine t. I'm going to call this one capital V of t. So 2 times omega crossed with capital V of t plus omega 0.1 t 0 cross quantity 0.1 t 0 crossed with the position, which was 0.5 plus 0.3 cosine of sine t, 0.3 sine of sine t 0. Okay, that does get pretty messy. That would be kind of a mess to, not horrible maybe, but kind of a mess to multiply out. But we're only asked to figure this out at t equals 0.5 seconds. So we can go back in and calculate what all of these things are at 0.5 seconds, you know? So at 0.5 seconds, oh, good Lord. Well, I'm not going to do that. But you would just plug in 0.5. These all have to be in radians. When do, like, it didn't say radians or degrees. When do you know that that functions are, like, functions with angles in them are given in radians? And when can they be given in degrees? If you're taking derivatives, it always has to be in radians. I'm sure there are other times too. But like in this class, that's the significant thing. The reason taking derivatives means you have to be in radians is because of the chain rule. You're going to multiply stuff from inside the arguments to the outside. And that's where things would go haywire if you had it in degrees. Okay? So anytime, if you're dealing with derivatives at all, you're just going to assume, unless it's explicitly said otherwise, you're going to assume that stuff is in radians. Yes?
Could you scroll back down to the acceleration?
This one?
Yeah, thank you. Yeah, that's right. Yeah.
Mm-hmm. So I guess this is maybe the first example we've done in class where you're going to use that, think of it in terms of that dot notation. So plug it into each function and you'll get a numeric vector as an answer. You won't have any more variables in there. Any questions about that one?
And so that would be at this one instant. So would this. So
Right. So if you multiplied this all out, you'd get an expression for the accelerations of function of time. And that's a really powerful thing to have. I mean, not in this case, because I just pulled this stuff out of the air, but if it's a real thing that you're trying to calculate, that's really powerful. Having, like, the most power you can have is having a function of time, you know? But this problem just asks you to evaluate it at a single instant. Any other questions? Okay, and then now number 5. Insert picture. Desktop. Okay, so at the instant shown, the disk is rotating at -5 radians per second about y, and an angular acceleration of +10. And at the same time, the rod rotates about its hinge with a constant angular velocity of 8. And so we're going to assume that's in the positive z. And then those are the radii. This is one where nothing's given as a function of time. So we're going to just think of this as the acceleration. And we're trying to calculate at the end of the rod. Okay, so first, part A. So first we're going to use a coordinate system at the calculate the acceleration at the end of the rod using let's do B first. B is the easy one. Let's save up for the hard one. Okay, so the acceleration of P is the observed acceleration of P plus omega dot cross P plus 2 times capital omega cross observed velocity of P omega is, so 0, -5, 0. And omega dot is 0, 10, 0. And at this instant, P is, what are those sizes? 1.5 and 1.3. So we got -1.5, +1.30. And now we have to think about, now we're thinking about the observed velocity and observed acceleration. So now we're going to forget that the disk is moving and just think about the circular motion of that P in the coordinate system. The observed velocity of P is omega cross r. And omega is 0.008. And now the difference between R and P is that R, so P we did from the coordinate system. R we're measuring from the center of the circular motion to P. So that is just 1.3 in the positive y direction. Any questions about that? So I believe that is -10.4. And then the acceleration of P that's observed that's the watermelon equation. So that's alpha cross r, and that was a constant angular velocity, I think, right? Yes. So this is 0 plus 0.008 crossed with, I'm going to write this again. But all this stuff is just this. So we get 0, 0, 8 crossed with negative 10.4, 0, 0. And you get 0, negative 83.2. And so the acceleration of P is equal to 0, negative 83.20 plus 0, 10, 0 crossed with negative 1.5, 1.30 plus 2 times 0, negative 5, 0 crossed with negative 10.400 plus 0, negative 5, 0 cross quantity 0, negative 5, 0 cross P, negative 1.5, 1.30. Okay, well, let's take a second and multiply this out. Okay. Go ahead.
Your answer? Yes.
Okay, go ahead.
27.1015.
Anyone else have an answer? Is that match anyone? Let's just get confirmation. What did you get?
37.5, negative 83.2, negative 89.
That's also what I got.
37.5.
Negative 83.2,
Okay.
negative 89.
Negative 89. Okay. Well, if two people got that, let's use it. No offense, Fred.
I'm just weird. Yeah, that's what I got too.
Okay. Okay. So can anyone look at this? So now we're going to move the coordinate system over to the base of the arm and do this calculation. Is anybody so advanced at this stuff that they can tell me just at a glance what acceleration we're going to get for P with this new coordinate system? Yes?
It's going to be 37.5, negative 83.2, negative 89.
Yes, that's correct. That's right. Yes, exactly. So the acceleration is the acceleration. So if you do it right, you need to get it the same way every time. So now we'll go to part A. And this time, we need to do two things. So this time, when you look cold at a problem, like say you're in some lab and you're trying to, you're brought in as the big shot to calculate this acceleration, like we're not sure what we have to do. The thought process you kind of have to think is like, okay, is this an inertial coordinate system that we're using? There's two ways it can be non-inertial. The coordinate system can be rotating, or the origin can be accelerating, or both, okay? Now that origin is moving in a circle, the origin is accelerating in addition to the orientation of the coordinate system changing, okay? You follow the distinction on that? So how are we going to take that into account? Well, we have to do it kind of in two steps. First, the acceleration of P relative to the ground is equal to the acceleration of P relative to the coordinate system, or let's call it the origin, plus the acceleration of the origin relative to the ground. Okay. This is just the acceleration of the origin. This is assuming that the origin isn't going anywhere, and this is using a rotating coordinate system. Okay? So let's first do this part. So kind of what we're doing now is we're ignoring for a second the acceleration of the origin and just calculating the acceleration if that point was fixed. So really you could, so like if this point was fixed, but the whole thing is still rotating with our given like rotations about this point. So you can imagine it'd be like this sort of swinging around that point, and this is turning around. Okay. Okay, so the acceleration of P relative to the origin is the observed acceleration of P plus omega dot cross P plus 2 times omega cross observed velocity of P plus omega cross quantity omega cross P. The rotation of the coordinate system is the same as it was in the first problem. I mean, the axes are changing orientation at the same rate. Okay, so our omega and omega dot are going to be the same, capital Omega and capital Omega dot. So we have omega is equal to 0, negative 5, 0. And omega dot is equal to 0, 10, 0. And now here's the first thing that's different, the position vector of the point P. Well, now we have a new coordinate system. We're using the one at the base. So the position vector is just going to be what was our R vector before. It's just going to be 0, 1.30. Any questions about that? And now we'll calculate the observed acceleration of the point P. So to that coordinate system, that point P is still in circular motion about the z-axis. And so the observed velocity of P is, it's omega cross R, little omega cross R. Omega is the angular velocity of the coordinate system, which is 008. Nope, 080. Is that what I used before? Oh no, little omega, I'm sorry. I got confused for a second. 008, okay. 008. And then R is the vector from the center of the circular motion to the point. So what's that? Yeah, it's the same as the position in this case. As I keep saying over and over, that's not always the case, but here it is. Okay. And So we get negative 10.400. And then the observed acceleration is watermelon equation. Alpha is 0 plus omega cross quantity omega cross r. And so that is 008 crossed with negative 10.400. And that's the same thing we got before for the observed acceleration. 0, negative 83.20. Okay? Yeah.
So when we're finding the observed velocity and acceleration, do they always share like the same omega and r?
Yeah.
Vector. So
Yep.
they share all the same vectors, and is that typically always how we find them? We're going to end up using the omega cross r and the watermelon.
Omega, yeah, exactly. That's always how you do it, unless you're given something as a function of time, and then you'll do these as the derivatives of the components. So there's only two ways you do it. You either use derivatives of the components of the position vector, if you have functions of time, or you're using these circular motion things. Yep, exactly. All right, now we can put all this together, and remember, this is just the first piece. So the acceleration of P relative to the origin is 0, negative 83.20 plus 0, 10, 0 crossed with the position vector. Yep, that one's 0, yep. Plus 2 times 0, negative 50, crossed with the observed velocity vector. Plus 0, negative 50, cross quantity 0, negative 50, cross position vector 0, 1.30. And these are parallel, so this whole term goes away. And so what do we have? The acceleration of P relative to the origin is, move this down a little. Ooh, sorry, say it again.
0, negative 83.2, negative 104.
104?
Yes.
Okay. So now we have to calculate the acceleration. What's the piece that we're skipping so far? We have to calculate the acceleration of the origin relative to the ground. Okay. Well, that's just a simple circular motion problem. We've done that a million times. You know, now we don't care about the arm. So the acceleration of the origin relative to the ground is alpha cross r plus omega cross quantity omega cross r. Alpha is equal to 0, 10, 0 Omega is 0, negative 5, 0. R is negative 1.5, 0, 0. And so the acceleration of the origin relative to the ground, 0, 10, 0, cross negative 1.5, 0, 0, plus 0, negative 5, 0, cross quantity 0, negative 5, 0, cross negative 1.5, 0, 0.
$37.50.
37.50 and 15. And so the acceleration of P relative to the ground is 0, negative 83.2, negative 104, plus 37.5, 0, 15. And you get 37.5, negative 83.2, negative 89. Is that what we got before? Do those look familiar?
Yes.
Yeah.
I can't believe Sam was able to calculate that instantly.
Yeah, exactly. I know. It's amazing intuition. So, I mean, honestly, I still, when I do that, I think it's cool, you know? I mean,
So I have a question for you.
yeah,
In this case, and the other things I pressed around, like the only variable I changed was, the P vector.
yeah.
And then you just do relative motion. Is that the case every single time? Or is there any other, is there situations where you would have to have, because, you know, this time all we did was change the P vector and then.
I've honestly never thought about that before, but I think you're probably right. I mean, none of the angular
Yeah, I thought.
stuff changes,
Yeah.
and the circular motion of the point you're looking at doesn't change, so I think that's right. I think you're right. The only thing that changes is the position vector, and then you sort of account for what that changes by adding on the acceleration of the origin.
Well, can you go back to the acceleration equation that went to 0?
Yeah, where was that? Here?
Yeah. It's the parts of the watermelon equation.
Yeah. Uh-huh, that's true. Yes, you're exactly right. That's funny. I've learned a lot here today from you guys. But, you know, so, I mean, this says, you know, the basic idea here is like, in a problem like this, you're totally choosing your coordinate system and you're just choosing it in a way that breaks this up into two simple motions. So you can put stuff anywhere. But you can see the implication of this is like, you tell the experimental engineers that you're working with, the experimentalists, like, I need to have position data taken over time from a coordinate system here. And then they try to do it, and then they're like, we can't do that. You know, there's something obscuring our view or whatever, but we can put it here. You can adjust all your calculations so you're calculating the exact same stuff.
Mm-hmm.
Any other questions about that? Okay. Well, when you do problems like that, I think you should always take a second to remind yourself how cool it is. Okay, well, let's stop there. And so Friday, we'll start with 15 minutes or so from Twin Cities Engineering. And then if you have any questions related to the test, I'll answer those. And if not, we'll finish up with this and probably next Monday, start with the next topic, which is vibrations.
Does anyone grab a